So before we go about how they die, before you start describing how anything dies, you have to first describe how you can define death. Like when it's a human being, suddenly doesn't move, doesn't breathe, okay cool, it's dead. You can't say that with a star, because star is not breathing in the first place. You have to explain how it dies, right? So the thing is, once a star dies, it still lives on. Like something else happens to it, changes to something else. It's not like the star dies and immediately nothing is there now. That's not how it works. So once a star loses its energy, loses hydrogen, and then it dies, it becomes something else. Like it becomes some other sort of form. So today's lecture is going to be using minimal mathematics and trying to explain to you what all possible things happen, how those things happen, and hopefully by the end of this session, if you are a CFET member or someone who is interested in astronomy, I want you, next time we are holding some sort of sky session and everything, to also think about like what star you are looking at. Like we show you like, okay, you're seeing this star, this Betelgeuse, this is Parker Orion and stuff, but unless you know what you're looking at, those things don't really have any sort of meaning. So that is the point actually. So yeah, before we talk about beyond the main sequence, post main sequence basically, first we have to talk about what is main sequence, because otherwise what is post without the main sequence is. So anyone has any idea what this is supposed to be? Anyone? If you don't know, it's fine. I'm just trying to get a gist. Any idea? Okay, cool, awesome. So I get to explain it. So basically, stars, what happens is, you know that fusion happens inside stars. Okay, so generally what happens is hydrogen gets turned into helium. This is the main thing that happens in all stars. We cannot replicate this on Earth. Mostly we can, but like not sustainably because of the temperatures inside the stars. And when like the Big Bang happened, the constituency of the universe is like 99 something percentage of hydrogen only, nothing else. And remaining 0.01 is helium and lithium basically. Nothing else was there apart from hydrogen. So when you're talking about stars, they are almost exclusively, completely hydrogen. So what happens inside a star is, if you have a star like this, the best circle I've ever had. Anyway, this is huge. Like seriously, stars are huge. The point is, you know how gravity works, right? Like, it wants to put everything towards the center and make it always small. So what happens? There is always going to be some force acting like this. Okay. Now what happens? Imagine I take like all of you into the room, close the room, and then suddenly started like shrinking the room. You will have like more pressure, more temperature, obviously, because it's like getting crammed in here. And because of this temperature and pressure, hydrogen becomes helium. This thing happens. This is not infinite. There is a limit. You cannot go forever making hydrogen into helium, because even though there is a lot of hydrogen inside the star, at some point it finishes. This is what happens. So my lecture is going to be focused on what happens once it finishes. So this diagram here is actually what you call HR diagram. So what happens is, I can just show you here as well. So this is basically all the dots that you see here, orange, blue and everything, are stars. Okay. So yeah, we have this rule called Wayne's displacement law, which is lambda, wavelength times temperature is a constant. This everyone has learned, in 12th standard. This constant. Okay. Now, if I am drawing a graph in terms of wavelength, or if I am drawing a graph in terms of temperature, it is the same thing. It is still constant. So this graph is actually temperature increases this side. So when something is like hot, it becomes red color. When something is like really hot, it becomes blue color. And that is why here it is red, and as you go towards the right, the star becomes blue color. The temperature is more and more basically. This is the temperature, increasing towards this direction. So this direction is basically the luminosity. Luminosity means like how bright a star is. So generally the rule of thumb is, if something is very bright, it is also very hot. This is the general rule. As you can see, when temperature increases, it is also blue color. This is the general rule, okay? And then backwards also. But then there are all these things here. These don't follow the thing. This line you see here is main sequence. These are all the stars that are taking hydrogen and making them into helium. The moment it runs out of helium, it goes here, it goes here, it goes here and stuff. So this is the main sequence that I am talking about. And what I am talking about is like what happens once it leaves. So the reason I am not taking like main sequence is because to completely understand main sequence stars, like there are not a lot of different types of main sequence. It's like mass is there, it is bright, cool, now you have stars. But apart from that, if you have to completely understand the evolution of like normal stars, you have to have a proper understanding of this graph. Like everything will be taught like, okay, line comes here, do this. If I start talking with that, immediately everyone will just get out. So the point is, I'm talking about what happens once it leaves, because there's a lot of cool things there. So this is the main sequence. Does anyone have anything like difficulty understanding this much? No, right? So my question is, what happens when this leaves here? Okay. So basically, when we're talking about post-main sequence, what happens afterwards when hydrogen is finished and there is helium, depending on the mass of the star, basically 0.8 to 8 solar mass. This thing basically means solar mass. Like how do I explain this? Centimeter, you have a definition, right? Meter, you have a definition. This dot basically means solar mass, which means 8 times the mass of the sun. Okay. If it is something along this, right, it becomes something called a red giant. Now our sun is obviously going to be 1 solar mass because this is based on it. So we are going to be a red giant. No, we, not we. The sun is going to be a red giant. And then after that, it becomes a planetary nebula and then a white dwarf. So my focus will be to go from here to here and then talk about this to this. Complete index you get about. Okay, now get ready. So the point is red giant. Okay, so our sun, obviously, if you look at the graph if you look at this, okay, our sun is somewhere here. And you might ask, oh, very nice coincidence, it's exactly in the middle. It's not. The reason why it is there is because the graph is based off of our sun. Okay, we are dividing by our suns, that's why it's somewhere in the middle. It's not basically red giants. Okay. So what happens when our sun or suns that are comparable to ours reaches the end of its stage and there is no more hydrogen inside? Well, there will be some hydrogen, but the point is like it's not enough to sustain a fusion. Okay. Think about this. There is some force acting inwards and there is some force acting outwards. And suddenly the force that is acting outwards becomes non-existent. Now what happens? Obviously it starts shrinking, right? So then the temperature increases again, the pressure increases again, and then that time what happens? The helium fuses to higher elements, basically carbon and all. This happens, and because of this, the star expands again. Now the star is relatively light. It is almost not like very light. Obviously, when we look at our mass in the sun, it's a huge thing, but relatively in terms of stars, this is light. So what happens? Imagine like you take some ball, you tie it to a string, you throw it very far. There is a limit, like you can throw it this far, the string will pull it back. But if you throw it beyond that, that thing will like break and go away, right? So similarly, when helium fuses into higher elements, the star expands. Okay, it really expands like this. This is our sun. It becomes like this big, basically. Like the sun exists now. When it becomes a red giant, the size will be enough to cover the orbit of the Earth. We will be in the radius of the in the diameter of the sun, basically. Point is, all the outer layers that are here, gets thrown away. It goes away because the mass is not so high that gravity will pull it back again. It slowly becomes like outwards, and this is what they are calling planetary nebula. Similarly, because of the fact that this has expanded, obviously the temperature is going to be cooler than the original star. So all this happens. This is what happens when a red giant is there. I think I have a photo. Yeah, you can see. This is what happens. Like you can see this. This is basically a sun and the star, and then this is the outer shedding layer. All of this would have been part of this at some point, but because of the fact that it contracted, made it into helium. Helium, again fused into something. It went out. So now you have something back here, and the thing that is remaining is actually the core of the original sun. That is there, and that is what will be remaining at the end of the day. Till then, everything else will be gone. This is called a planetary nebula, actually. Like all the thing that is like here, no, it's a planetary nebula. Doesn't have anything to do with planets. When we first discovered it, we thought it had something to do with planets, so we call it planetary nebula. Realized it doesn't have anything to do with planets, we still call it planetary nebula. Why? So the point is, once that happens, this core, this remaining core, this is what a white dwarf is. This is the eventual ending of stars like our sun basically. And this is going to be like roughly the size of Earth. Sun is like 1.3 million times or something the size of Earth, right? Replace that with something the size of Earth. But the density is so huge, it is, I think, I'm not exactly sure, but of the order of 10 power 11 or something like that, kilograms of merit. I'm not exactly sure. But the point is, very dense, remaining thing. This is the core of the sun. Now think about this. Initially, you ran out of hydrogen and helium. And that is what this thing is. Now this thing also has gravity, no? So this thing also should collide, like go inside. So something has to be putting pressure outside. Otherwise this also would go back to like singularity basically. So the way this works, and this is where the only physics part of the thing comes, okay. So you guys focus a little bit, you should be able to understand. You guys know what Pauli's exclusion principle is? You guys have all heard of it. If you don't know, two electrons cannot in an atom cannot have the same set of 4 quantum numbers. Simple. You guys also know what Heisenberg's uncertainty principle is. You cannot say position and momentum with absolute precision. It has to be greater than h1. Awesome. If that is the case, I think I put it somewhere else. The point is, if this is the case, you have a very small area. Okay? You have a lot of atoms in that area. I told you the density is very, very high. Generally, when you are having a material, the electrons also have the freedom of going around the surface. It doesn't necessarily have to be always within the atom itself. It has the ability to be a sea of electrons basically, especially in metals and stuff. But in the star, even if the electron wants to leave the atom, there is no space basically. So imagine you're like properly making very dense thing. The electrons cannot go anywhere. So what happens? Obviously, the electrons have to take the lowest possible orbit. It always takes the lowest orbit. So if this is the nucleus, here one electron, here one electron, here one electron. Think about this. You know that this is full. So then this also is full, and it is not going outside anywhere. So now you know where all the electrons are. And from uncertainty principle, if I know something where it is, then I don't know what?
Momentum.
Momentum. Okay. And so that momentum is p squared by 2m gives a kinetic energy. And that pushes the star outwards, basically. So you have gravity acting inwards, but you have electrons that are pushing it outwards. Because of the fact that there is not enough space for it to be random, basically. So the electrons are pushing. And because of this, there is no fusion happening inside white dwarf. The only thing that is happening is a bunch of electrons just going, to get out. And because of this, white dwarfs are very, very slow in losing its temperature. Theoretically, we have no proof of this. We are saying that over billions and billions of years, it will become something kind of black hole. But we don't know because our universe has not existed long enough for this to happen. This is theoretical. It might happen. It should happen. Like electrons are so packed together that they can't radiate energy. They have to push energy out, like through convection. The point is, it is so it's theoretical. We are not sure. It probably will happen at some point, but our universe is nowhere old for this to happen, and most likely you won't be able to see it also because again, this will take billions and billions of years. Again, I put in here that it occupies the left bottom of the exact diagram. You can see it here actually. This part. This is what a white dwarf is. It is extremely hot at the same time not bright at all. Okay. Yes. The other thing is classification of spectra. So you guys know what spectrographs are. Material science. You guys have to be using this. Who was material science? You guys have to be using spectrographs. You know how spectrographs work. Every atom has its particular spectrum. So when you are looking at a star and you see a particular spectrum, then you can classify it. And so depending on what you are seeing in it, then you can classify the white dwarf. If it is Da, then it has hydrogen in it. If it is Tb, it is helium. The point is, at the end of the day, even though hydrogen did run out, there will always be some sort of hydrogen left. And because of that,
so why is it Da, Db, Tc and all?
I have no idea. It is what the classification is.
So it's just a convention.
It is a convention basically. So the point is, it's DC means that it doesn't have any sort of atomic spectra, DQ means carbon spectra, DZ means metal. Actually, when you're talking about astro, X, Y and Z, these are three variables that we use where X is always hydrogen, this is always helium, and this is always metals. So I can explain why DZ is metal is because generally they do use Z for metals. And when we are talking about, okay, when we are talking about metals, what am I saying? Everything about helium. So when we are talking about materials, we are talking about 21 and above, right? Periodic table. But in space, like I said, only hydrogen was there, some helium was there. So everything about that is considered metal. Okay. So when I say metals, you have to understand that like this is what I'm saying. The point is, have one more slide somewhere. Yes, this is what I was saying. The how electrons are basically pushing. The other thing that is actually very cool about white dwarfs is that they obey one relation where mass times volume is a constant. If mass increases, what will happen to volume?
Decreases.
Decreases. Which means a more massive white dwarf will be
Less of volume.
less volume. Which means if I have a really massive white dwarf, then it has
Emptier.
and basically. Now if I have an infinite, this has to go to 0. Okay? The point is, there is a limit called Chandrasekhar limit, you may have heard of it. Once that this mass is above that, the volume becomes so small that it can actually become a black hole. So, even though I am explaining these as like separate things, like okay, supergiant will become black hole, this will become white dwarf, these things are not mutually exclusive. It is not that like if I have a white dwarf, okay, and if I have another white dwarf next to it, and if they collide, they can form a black hole. They can form basically because of the fact that the mass will become more than that, volume will decrease also. So, any questions about white dwarfs?
How would you get temperature?
So the thing is like initial because of the thermal motion of electrons only, nothing else. And because of that, like they are very hot, but they radiate it very like poorly. And because of that, they take a lot of time to leave the heat like from the system. Because of the fact that it is like so properly put together, there is no space for the heat to radiate outwards itself. So it doesn't radiate heat, but it is hot. That is the thing.
How do you define hot here?
Hot is like kinetic energy of the electron. Like it's obviously it has heat. That's why it is pushing outward, no? And gravity is pushing inward. So there is definitely temperature, like heat is there, but it doesn't radiate it outwards efficiently. It does radiate it. It takes billions of years, but it does do it, but very slowly. Anything else?
Like white dwarfs are hotter than our sun, or it's cooler
Yes, it
than
is
our?
hotter actually. Yeah. So I'm not sure if it is hotter than the core of the sun, but you do realize that this was the core of our sun. And surface temperature of sun is around 6,000 Kelvin. But this will be like millions of Kelvin. But that is because the core of the sun is also of that temperature. So I'm not sure which would be like more hotter, but the point is
Comparable.
comparably surface temperature obviously white dwarfs will be more because this was the core at some point. Anything else?
So in the normal, the first main thing, so the hydrogen is there. It is used to create helium. But helium is heavier than hydrogen.
Yes.
It should go to the core of the body. But then fusion won't happen, right? Like, because the core is filled with helium.
No, helium can fuse into higher elements if given enough pressure and temperature.
Yes, like, for example, the initial, like, first, the core will be filled with helium, right?
Yes.
In the first few, I don't know, minutes. So, like, does, like, the helium radiate out? Like, how does the fusion happen after that?
Right, so basically what happens, you have a sun, okay? Now hydrogen ran out, so it contracts.
So, like, say, the first helium atom. The first helium atom occupies the center of the mass. Okay. Now, center of mass is occupied by helium, so there is no. So gravity is acting on the helium. So, like, what happens then? So there is no hydrogen in the center.
You're saying like what? Like just two hydrogen is done and one helium is there. So you're saying now like there is one helium.
The center is now occupied by helium.
Not just center. No, the center has all sorts of like hydrogen. There's like a lot of hydrogen and helium in it. No, it is not countable number. No, I don't understand like your question exactly. Let's make it a problem.
That's fine.
No, like you can ask, but what I'm saying is, even though there is helium in the core initially also, like obviously if I start the sun right now, it has formed helium. But the point is that there is not enough pressure and temperature for it to form.
But where is the hydrogen fusion happening? Because the center is occupied by helium.
No. Initially this is fully hydrogen. Okay. Now when this is like filled with hydrogen, what happens after enough time? Hydrogen dies out. Then you basically have something called a hydrogen shell basically. here.
Mhm.
But now the volume is filled with helium.
Mhm.
And then since it is a red giant, it comes down like this, and then this helium basically forms into a next element. When we go into supergiants, you will see that this happens, star contracts, becomes more pressure, and then helium forms a core, and then now you have another like element inside. Understood? Like somewhat?
No, but my question was like, after the first fusion,
Huh.
helium occupies the center. So the fusion happening at the center of the.
You can't say center, no, because it is not like it is happening in one center, everything is happening there. It's like there is like millions and millions of
So
like.
there is like a volume where the fusion can happen.
In the core of the star. No?
So core is like a big volume, like it's not a point.
No, core is not a point.
Okay.
Core is like I said, white dwarf is around 7,000 kilometers long. No? So that much space is there. It is not a point.
Fusion can happen in any.
It happens everywhere. It's not it can happen, it does happen everywhere. But at the end of the day, what happens? Hydrogen forms a shell by the ending and then helium becomes the center. Anyone else?
Why is mass involved in constant?
Right, that's because of the fact that there is an upper limit to this. Like the mathematics actually gets a bit complicated, so I didn't put it here. But the point is, once it gets so massive, the volume actually reduces. Like there is a limit to what something can be considered a white dwarf. If it is even more massive than that, it bends space-time, becomes a black hole basically. It slowly converts into a black hole. So there is an upper limit. So that upper limit is why this relationship is there. Radius and mass are related to each other basically. Inversely related. Yeah.
So white dwarfs lack singularity.
Yes. There is no singularity. But if you do keep increasing the mass, at some point you will get a black hole. Right? Anything else? I'm glad at least something is understand. Like if you're asking questions, then something is like teaching. So next is supergiant. Okay. So we talked about this part, right? This part we completed. Okay. Now it's this part basically. So when we go to supergiant, basically it is like a red giant. The only difference is that the mass is much higher than what our sun is. And similarly to what happened with our sun, we used to be in the other classroom and we always hear this sound like from here, and our professor would be like, what is he doing with the board? Now I understand. Okay, so the difference is basically, unlike red giant, supergiant, if you consider a supergiant with a red giant will think supergiant is much bigger giant. This is the problem, this is the difference basically. Simple thing. So this will be like greater than 8 solar panels. Okay. Again, this also will be, if you look at back at the, you can see it over here. This is where supergiants are. The point is, what happens is similar to red giant, same mechanism, no difference. Okay. So what happens? Hydrogen is finished. Okay. Teacher is closed for the hydrogen. Now you have a hydrogen shell. This thing starts contracting. This makes helium. Helium. Then what happens? This again goes out. Now, in red giant, this was the point where everything went away. But the point is there is so much mass in a supergiant that gravity will still pull it down. Okay, so now you have helium for becoming basically like helium to hydrogen, helium, lithium, beryllium, carbon, so let's say carbon. Okay, what happens? It pushes inwards. Helium runs out. Then it contracts again. So then now it starts making nitrogen, and then it again contracts. Then it makes the next thing. Then it makes the next thing. It keeps making the thing until it reaches what? Any idea? Exactly. Why? Most stable. Now the star is in trouble because now it can't do it. Till now it was like making stuff, and then now it reaches the point where it can't make it. This can't do it. Now what happens? This thing is huge. There is like so much mass here. So it basically in a second basically. It moves almost 0.25 times the velocity of light. Whoosh.
Nihal bhaiya,
Huh.
I doubt as a beginner I don't understand if I have a doubt that how are elements after iron created then?
He'll get it. Just patience.
Okay.
Just wait here. So this explodes. It's really cool actually because at the end of the day, space only started with hydrogen in helium, but in your blood there is iron, right? We have uranium for making fusion. Everything is there on Earth. So where did they come from? Really, this is really cool. Good question. So anyway, the point is, reaches iron. Can't do anything. Goes inside. And this core also becomes like, instead of circle, it's like, and then, okay. So what happens? You get this, basically. Supernova, basically. The death of the superstar. Now, what happens? This photo, again, if you go into space, this is not what it will look like. You guys know that, right? I'm sorry if now someone didn't know and I'm like breaking your reality here. This is a bunch of radiation that shouldn't be visible being made visible just so that we can see it basically. This is from an X-ray observatory. You cannot see X-ray, but they color it so that you can see like, okay, this is there. Similarly, this is a supernova basically. You now have some star that has exploded.
You say explode, but you just
Implode basically.
like implosion.
Implosion, no, because this is going inside and it bounces off the iron core and
Okay, so
Yeah.
it's first implosion and that causes that.
causes the explosion. Okay. So now there are two options depending on the mass of this. If the core's weight is less than 3 solar masses, it forms neutron star. If it is greater than 3 solar masses, it forms black hole. Okay. Again, these are not mutually exclusive things. If I have a neutron star that is like 2 solar masses, go and heat it against another neutron star that has 1 solar mass, then it can form black hole. So these are not mutually exclusive. So what I'm saying after supergiant, again, this is about observing these things. Okay. So supernova is basically the corpse of a star. You guys can agree there. Okay. Now what we are going to be doing is essentially looking at a dead body and saying what it used to do when it was alive. This is not something you can do with a human being, but you can do it with a star. I will explain. So what happens when you have something called type 1? Again, these are convention names. Okay, don't ask why it is 1, why it is 2. So I don't know. So the thing is, when it's type 1, there is no hydrogen. So if one star, also when a star is very big, it dies very fast. The formation and death happens fast. Smaller star takes a longer time to die. This part is okay. Now think about this. If I am looking at a spectrum and there is no hydrogen inside it, none at all, what can I say about this star? It used up all the hydrogen. Awesome. What does it say about the size of the star?
It will be small.
It will be small. Okay. Now you
Mass will be also high.
exactly. Mass will be small. Mass will be sun compared, solar compared. Like it will be big, but not like it will still be a supergiant. Then only it will become a supernova. But in terms of supernova, it will be a smaller star. So now you are talking about what the star used to do before it died. From looking at the spectrum of a corpse of the star. Now if it doesn't have hydrogen, now if it has hydrogen, what does it say? It burst before it finished the hydrogen, which means that it had to be a bigger star basically. And if you are seeing silicon in it, then you can say it used to make silicon. If you can see some, like if you look at spectrum and you see like different elements in it, you can say what was produced in that core of a star that is no longer there. You are looking at something that doesn't exist and you are saying like, oh, back when it existed, it used to be. It's a very cool thing if you think about it. Okay. Now, what happens? Supernova. Yeah, this is what I basically just explained, and then there are more classifications like type 2A, 2L, and 2P, which is basically if you are looking at the brightness of the supernova, L is linear, so it goes like this. This is L, and this is time on after the supernova, and then if it is 2P, it is like this. It has a plateau. That's why it's P. Point is, this all depends on the elements that are produced there and like half-life of those that radiate, and so you can see the luminosity and stuff like that. Not going too deep into it. Higher elements, right? So I don't think I have a slide on it, but obviously I wanted to talk about it. So neutron star you have. Now, before that, actually, we need to talk about after supernova, what happens basically, what is remaining after a supernova. And that is something called a neutron star. Why do you think it is called neutron star? What do you think is inside the star? Simple as that. So, yeah. The point is, supernova happens. Now, this is the core. Atoms should be neutrons, protons, electrons. This thing is the size of 25 kilometers. This was once a star that was millions of kilometers. Now it's 25 kilometers. Basically, the size of Hyderabad. How much space do you think it will have for atoms? Basically, nothing will. Like obviously, for one atom, space is there, lot of space is there. The point is like the atoms that it has, there is no space for it. What happens? Imagine this is a nucleus. Okay, there is neutron, proton, and there is electrons. All this become neutrons. Proton plus electron gives neutron plus electron. And that is why this whole thing is filled with neutrons. And neutron stars are similar to planets because it has an atmosphere like this. Okay? The crust will be formed by what element? What do you think? What element do you think forms the crust of this star?
Iron, I guess.
Iron basically. Because this was what was last time. And then inside it gets weird, actually weird. Because initially you used to have, like, I can draw right there. So, you know what? Like atoms are arranged in lattice, right? Like this. And when you look at here, it will be like that. When you reach here, this thing, no, it will become like this. Something they call nuclear pasta.
So lattice itself breaks.
Everything. There is no more atoms. It becomes neutrons, neutrons, and neutrons. Completely.
Structures get completed.
Point is, we don't know completely about because we can't look into the neutron star. But this has to happen. And the point is, this will be one of the most stable, densest things possible. And similar to how white dwarfs, there was electrons providing the energy by pushing out. In this, it is neutrons. Basically, neutrons also have Pauli's exclusion principle. It also cannot occupy the same quantum state. So now neutrons are giving the energy to push upwards. This is what happens. So, the other thing that happens is, you guys know how much the magnetic field of Earth is?
0.007 something.
Microfarad, microtesla, something micro. And for a neutron star, it is somewhere of the order of 10 quadrillion times Earth, which is very powerful. And another thing is, you guys know conservation of angular momentum. You spin and then put your hand together and you spin faster. When this thing is imploding, there will be some slight angular momentum given to it. Obviously, it's like so much pressure is coming from so much, little bit spin. And because of that, when the whole mass is gone and only this thing is remaining, the spin is very, very fast. It spins so fast that it might complete one rotation, maybe like in 3 seconds, 1 second, stuff like that. And I told you, right? This is like let's assume that this is a neutron star, and there is obviously magnetic field lines. Okay, and there will be magnetic field lines shooting like this. Okay, and imagine you are here, and you are looking at this. This thing rotates every 3 seconds. Now, if you are just taking a note of this, if you are drawing a graph, basically, you will see that it goes like beep, beep. This thing is so consistent that this is basically one of the, like, you can call them like universal clocks, basically, because they are so consistent and they don't change for like long time. They don't change that. And we used to see this, and I think initially, I'm not sure of it, but people did consider it like, oh, maybe we found extraterrestrial or something. But no, it's stars, doing stars. Spins very fast, very high and since it's stars, like it spins very fast and it's like hitting us with a magnetic field. We used to call it.
By the way, what phase of star it was?
Huh?
Is it a white dwarf or
No,
a supergiant?
white dwarf is completely exclusive.
Normal star or like supergiant?
Something massive than a sun becomes a supergiant, forms iron in its core, and then becomes this. Assuming the core was less than 3 solar masses.
Okay.
You get this. And we used to call it pulsars because it's like getting pulses. You're getting pulses, no? This magnetic field. So like if you set up an observation, you're just seeing like beep, beep. So pulsars, and because of its high magnetic field right after being made, it's also called magnetars. So, because initially we used to think that these are a separate thing, but in the end these are the same thing basically. So they do have different names, and I think around 2000 something pulsars we have within our own galaxy. So,
Do these also radiates neutrinos?
these radiate, again, these are also very bad at thermally, like putting out radiation, but it does send heat over, like again, very slow time periods, like very long time periods basically. Similar to white dwarfs. That is the thing actually. Usually we are calling this as dying of stars, but when you think about it, it's really not dying of stars. Because star lasted maybe 5 billion years, and this thing will be lasting like billions and billions of years. So is it really dying? That definition comes up to you basically, because this was like in a terms of like, it's like saying you have a baby and then become an adult. You're like, baby died. No, baby didn't die. This was the actual one. Baby was staged. But I have a question like this last 10, 15, thousands of times than the star actually existed. So like, is it dying? I don't know. So that's why I put the title as post main sequence. But we had to put dying stars, so people would be like, oh.
What is the cause of magnetic field? Because magnetic field are created.
Neutrons basically, like high magnetic properties. I don't know exact detailing of that, but because of the neutron, there is some superconductivity and magnetic field. I'm not exactly sure of the
Magnetic
mechanism.
field are created by moving charge particles. Right? So neutrons are neutral, so they should not be able to create magnetic field.
Yeah, I'm not exactly sure of that actually. Yeah, I have to look into it, but it does do that. That much I know. but I don't remember the exact mechanism of why it produces. But yeah.
Although there are neutrons have two protons and neutron stars, there are also protons and electrons present in the star.
You have this equation also, no? This proton plus electron gives neutron plus. This also does. This also will be radiating.
Smaller neutron stars, but it is not completely devoid of electrons and protons.
Again, like the crust of the star is still iron only. Yeah, there still has iron in the lattice and everything. Only inside the core it becomes like problematic. Anything else? Before we get into next. So one more cool thing actually. Neutron star, you have this. Cooler than one neutron star is another neutron star. Okay? This thing and this thing will be orbiting against each other. And what happens is, slowly they will lose energy. Because these things are so massive that the space-time around it will be like gravitational waves. You guys have heard of gravitational waves. It will be sending, basically. Initially, in the end, this goes and collides with each other and explodes again. Already this was created from one supernova. Then it went and exploded again. This time it is called a kilonova, basically. Kilonova, basically. From here, what happens? The explosion is again so strong that neutrons get changed back into protons and electrons, and atoms recombine, and this is where we get uranium and all the hydrogens. So all the elements that you see on Earth are not from the death of a star. It is the death of a star, then followed by another death of the same star. Two explosions back to back, not back to back, could be different stars. Point is, these send out the elements into space, and then at some point there will be some sun formed, and then there will be like a planet around it, and then somehow this happens. Okay, the point is.
I had a doubt. So if iron is like more stable, so elements after it, do they come back to iron?
No, they don't come back to iron actually. Only the radioactive ones. I mean, every element does have a half-life, but it does vary depending on the element.
Okay.
Just because it is above iron doesn't mean that it necessarily is radioactive. But it has its lifespan, like half-life period is there. So yeah, most of the elements like gold, silver, uranium, bismuth, all the other ones higher than iron are formed from the kilonova basically. Yeah, and then black holes. Okay, these are like the celebrities of stellar. That's why I only put one slide. So the point is, you all know what black holes are. Just for the sake of like, I explained everything. So. Again, the difference is, if it were greater than 3 solar masses, you get black hole. if two white dwarfs hit each other and they also have greater than 3 solar masses, they also form a black hole. Anything that in the end becomes greater than this becomes a black hole basically. And to be honest, they are not black holes. It is that the gravity is so extreme that the only way to come outside would be to go faster than light. And Einstein said, no. So that you can't get out. Even if someone falls into a black hole, you don't really see them like go into it. What happens is like you go there and then you slightly redshift and redshift and redshift. So the outside possible. To inside, you have a problem. Because it can be a lot of things. We don't have a proper theory of what happens inside a black hole. Okay. Again, there is not much for me to explain what happens inside a black hole because we don't know anything mostly. What we do know is like from our theories and observation, like almost all galaxy centers do have a supermassive black hole. That will be millions and billions of times the mass of the sun. I was talking about 3, and in the center of the galaxy, there is like huge supermassive black holes. And this also similar to neutron stars. You can connect all these together. Similar to neutron stars, these also have something shooting, X-rays and gamma rays basically, and it also has like accretion disk around it, like this. The other thing that is actually cool about black holes and neutron stars is standing here.
You said center of the galaxy, right? You are going to say why is it always center of the galaxy?
Because center of the galaxy is where most mass will be, no? By default. Because of gravity, most of the mass will be towards the center of the galaxy. So the star forming there will be heavier, and so there will be black hole formation. And if more stars die, again I told you, black holes can actually, like neutron stars can hit each other, become black holes and such. So that is why in the center of the galaxy it is there. So another cool thing about neutron stars and black holes are that standing from here, I can see behind the star, behind the star. So the reason for that is, imagine I am standing here. The only way I can see behind me is if light from here is somehow reaching here. This for me is important. I cannot do it. What happens if I remove everything else and go to the black hole? Light is coming from here, like let's say like from the accretion disk. Like there is an accretion disk around it. No? Like this. Say if light is coming here, because of the gravity it will get bent like this, and you will be seeing it from here. And this is why when you saw the actual photo of the black hole, it was not like this. It was circle and then it had like this. And the reason for that, this part is actually from behind the black hole. You guys have seen Interstellar, no?
Oh.
So you all saw that there's this thing, and there's this also. So what is actually happening is light from behind the black hole is actually showing up on this side because of the way light is being bent. Similar to neutron stars, they also do the same thing. So, yeah, the other thing again, I mean, you're not children, no? Like, last day we went to take class for some children, they're like, black holes will eat everything up, what will happen with it? Anyone has such doubts? If that is, again, I'm not joking, but the point is like that there is, someone actually asked, like, what happens? Nothing will happen. If you take a sun, remove it, put a black hole of a similar mass there, nothing will happen except we'll all freeze to death, but apart from that, nothing will happen. Similar, small problem. It won't like suddenly take everything. Only if you are within the region of like
Event horizon.
then only it will go inside. Otherwise nothing will happen. Anything? Any questions? Because after this there is nothing. So after this there is nothing. So if someone has doubts, anything else? There is about black hole.
Do space-time graph, whatever the says, do it bends near the black hole?
It does.
Can you explain to a certain extent how it works?
Okay, fine. So the way Newton described gravity is force. G/m by r square. You're standing, something is pulling down. The way Einstein explained gravity is very fun. So imagine you're standing here. One of you stand like maybe 10 kilometers away from me, and both of us start walking parallelly towards north. Here, I am standing here, you are standing here. Both of us walk parallelly. What happens in the end?
You both reach the pole.
Like this. How? I walked straight. He also walked straight. He or she walked straight. How did we intersect? Parallel lines are not supposed to intersect. Exactly. It is a circle. And if you walk parallelly on a circle, you will end up in the same place. But I walked straight. The other person walked straight. Somehow we intersect. Einstein said gravity is similar to this. That is, I am not rotating around the sun because I am orbiting around the sun. I am going straight. But it is that the sun is making the area around it spherical such that when I am going straight, it's actually spherical. So what happens? And then you see the basically like this great structure and everything basically. I get massive oversimplification because this is supposed to be 4 dimension, drawn as 2 dimension, one of course. Point is, this is not how it's supposed to be. It's like 4 dimensional structure. The point is, when something is here, it becomes like this. Such that, according to this thing, no, I am still going straight. I am still going straight. It is that the like space itself is curved. So I am walking straight. But since this whole thing is curved, it looks like it is in a circle. So this is what happens. This is why it's called bending of space-time. Like if a black hole is there, and we usually explain the pull of something using the depth of the. So that's why black hole you see that beam you guys have all seen. No? It goes like this. This is what a black hole is. Such that here also, if someone is moving straight, not because it is pulling in, but because the space itself is curved. This is what the difference is, and I hope that clears it.
How do you distinguish between a normal force and like the space itself is done?
Yeah, so basically the problem is like initially our theory of gravity was that it is a force. Now it is basically that it is curvature of space. And now particle physicists are trying to find particles for gravity. It is all work in progress. At some point maybe we'll have some better idea. But the point is, the reason for force, this explains it better. It's more complicated maths, but it connects time and space as well. Newton's force doesn't do that. Here now you finally have like something that is going here. When you get here, time also gets affected. So that was not possible for Newton's theory to explain. It gave a very intuitive, very simple picture, but this explains it better.
So are all forces like this or just gravity?
Gravity.
Just gravity.
Yeah. Only gravity is working like this. All the other forces have forces, are forces. This is also called force of gravity, but it can be explained better like this. And curvature of space is something that we can detect, because when neutron stars go next to each other and orbit each other, this does send a wave. Like if you have a cloth and you do this, that similar type of thing actually approaches us, and we detect it and we do studies on it.
Because of this only the time relation happens, right?
Yeah, because that is another thing basically. So when you are going near something, general relativity. Completely we have done from the topic, but it is fun, so I'll explain. When you are near something massive, time goes separately for you, as if you are, and if you are away from something, time goes separately for you. It is how it works. If you are going very fast, time slows down. If you are standing still, time slows down. It's normal. Normal is relative, basically. Point is, even being on Earth and an astronaut in space has different time. But it will be of the order of nanoseconds. It won't be. And I know, like generally people say like, oh, relativity, like big thing. You never use it. But the point is, if we never accounted for time dilation, your GPS would never be able to show where you are. Because that accounts, because satellite is in space. It has a different clock than yours. There is a nanosecond difference, some small amount. But the point is, that difference will be between you being here and in actual hydrogen. There is a reason. You have to account for these things when you are actually doing stuff like this. So this is why time slows down. When you are actually near something massive, time slows down. Black hole is so massive and infinitely small that it distorts time so slowly that if you actually went near a black hole, purely from a general relativity sense, you will see the universe fast forward. Because time will be basically slow for you, so slow for you that you will see everything else happening. But for everyone outside it will be looking like slow, like normal time passing. Similarly, another thing is, when you are approaching the velocity, if your velocity is approaching the speed of light, time slows down. If you are a photon moving at the velocity of light, time doesn't exist. Like this star leaving this light, it doesn't have time. For it leaving this and hitting your eyes happen at the exact time, because there is no time for it. There is no time because it is moving at the speed of light. Okay, when it enters the Earth's atmosphere, there will be like some distortion because of that. There will be like some. But in vacuum, if you were in vacuum, it was in vacuum. There is no time between when it is released and when you are seeing it, basically. So that is it. And then I just have one slide here, which is basically what it means to people who are observing. So when you are like when we conduct sessions, we do say like, okay, we are looking at Orion Nebula, we are looking at this star, that star. But again, it doesn't really mean anything, right? Betelgeuse is a star. You guys know where Betelgeuse is supposed to be? Non-Cepheid people. You have to know. But you guys have seen Betelgeuse, a star? One like if Orion is there's a constellation called Orion. I know like 3 constellations. Okay, so for me this is the go-to. Point is there are like stars like this, like I'm serious. I'm really bad at memorizing. It is somewhere here. Okay, this is orange color. This is a red giant. If you look in the telescope, it is red color. It is variable also. There is a chance that within our was it a red giant or super giant? I don't know. But the point is, within our lifetime, this thing will have a very high probability of exploding and becoming a supernova, such that it will actually be almost as bright as the moon in the sky. Now imagine next day you're going. This can happen anytime. By the way, there's no nothing to say like it can. No, it can happen anytime. You go outside, you see the sky. Suddenly there is something as bright as the moon. What do you think? Like people will react? How do you genuinely think? People will start panicking, thinking the world is ending. Actually, but knowing this, you should be able to say this is something that is supposed to happen for that star. This is the point. I want you to connect whatever theory I have given here to see what you are observing in the sky. So like Betelgeuse is there. Okay, so what happens to it? Why is it exploding? Well, it is in the red giant phase. Obviously, at some point it has to send out the planetary nebula and become a white dwarf. So at some point it will disappear from the sky. That can happen within the next 100 years also. It can happen. It is just gone. You can't see it in the sky anymore. Gone. So obviously people will be like, oh, I remember back in the day one star was there. Point is, I want you to connect these two things. When you're looking at Sirius, you should be able to tell like what star is this. Sirius is also, I think, a binary star system. So there is like one more star attached to it. I think one of them was a white dwarf. So you should be able to connect all this. This is what I'm trying to say. Like, here is one thing, and then we are holding observation sessions. People will show up and they actually ask so many questions, but then they are not able to connect it because they don't know what is happening behind it. So I want you guys, now that you know all these things, the next time you want to start a session, you should be able to say like, okay, this is what is happening. It's in this stage. Okay, like roughly. Why if you don't have to by heart it, you can just like, okay, then you observe the star, just Google like what classification it is. You have an idea of what it is, where it is going, what is going to do. In the future you can tell. If you're looking at a nebula, you can say, okay, what is going to happen. If you're looking at a supernova, you can calculate what happened. All these things. These are the tools basically. Now your job is to basically go and use it. Okay, I think with that my session has finished. Yes. Any questions?
How different was the night sky for our ancestors?
It will be different. Actually, we had this crab nebula, right? This crab nebula. No? This actually happened within the last 1,000 years, and there are written records of this happening. They call it visiting star or something like that. Like it actually happened, and there are records of like Chinese and Arabic and all. They're saying like something appeared in the sky. This happened before. So there was a star here that we can't see anymore. So it is different. Like obviously the spacing of the stars are not going to change much in terms of human lifespan, but the stars can explode and they can disappear from the sky. Limited edition basically. So some
So the sooner it means in like human time or like in astronomical time?
What do you mean? 1,000 years?
No, like you said that it may explode any time.
Yes, in human time. It can explode in your life. It can happen. Couple of years ago, people thought it almost exploded because it is a variable star. Basically, it is like releasing and then becoming like releasing stuff. So it's in that red giant thing. At any point, it can happen. Within the next 100 years, it can happen. So that is